So let's talk about global stability quickly. So we have this control. This is the Lyapunov function. We've already argued this one is definitely radially unbounded. So if sigmas go to infinity, del omegas go to infinity, this always keeps going off to infinity. It's good for any initial states. And that is good. And the v dot was minus p del omega squared, also globally negative semi-definite. So we do have a globally stabilizing system at this point. All right? But it turns out we have made no arguments about convergence. We don't know if it converges or not. It will, but we have to do this. So now switching was something we talked about, right? So we do have to switch. And this was the classic thing. There's two possible MRP sets. One describes the short rotation, one the long. We like to switch when sigma squared goes to 1, because then 2, at least my v function will be continuous. So I have to switch to a little bit different theory from Lyapunov. There's something called switched Lyapunov theories, where you have competing Lyapunov cost functions of your control tracking errors. And then you can switch between them to develop these controls. I'm not going to go through all the details of that, but the continuity is one of the important parts. And so switching here at 180 from a control is very, very nice. But the other issue is we needed, with Lyapunov stability, continuous derivatives, right? We don't have that when we switch. We're jumping with those, so we violate that agreement. But with additional arguments, until I tumble 180 degrees, I know I am perfectly stable. In fact, I've guaranteed that. And I've decreased energy. And we can also show we'll be asymptotic in that sense, too, in a second. But we know we're going to decrease our Lyapunov cost measure. At some point, time v1, we've reached this. Now we switch. Our v function, which is continuous, which is a key, is good. So the cost error is the same, but all of a sudden you might have a discontinuous v function because we switched the derivative. So it's no longer smooth. But you can switch over, and then it basically becomes a new problem. We're resetting our control. We ended up with plus 180. I do a switch. Now I'm controlling it minus 180 because I'm going to complete the revolution that way. And then once we made the switch, your stability arguments still hold for the next set of it. So by breaking up the total control performance into discrete steps of, up to the next switch, then the next switch, the next switch, all those arguments hold. And through continuity of the v function that we have here, we can still guarantee global stability of this system. So that's with the switching. I can show you graphically why this is important. If you have a v function, let's just have sigma as a scalar and v, and I'm starting out here and I'm making it smaller. You can have something where v dot is always negative. I'm always dumping error. I'm dumping error and dumping error. And then I switch. If you don't make this continuous, you could have something that switches to a higher level, and then you make it smaller, and you switch again to a higher level, and you could actually, well, I started up too high, but you could actually increase and make it worse and worse and worse. So every time after switching, you guaranteed to make it better, but the switches itself could make these measures much worse in how you're describing. So mathematically, this can happen. But in our system, we're guaranteed that my v function is continuous, so I haven't made my error measure any worse, and I may have a kink, and then I go here, and then there's another one, and then it's going to settle in. And because you have a finite amount of energy, we can also prove with passivity, this thing will continue to dump energy, dump energy, dump energy, and it will converge. Ansel.
Do the resulting controls also look linear? I mean, continuous?
No. The control would be discontinuous. So the control here, if you plotted this, you would have some control, and then all of a sudden it does something else, and then it does something else. So if you're worried about discontinuous control, what we typically do in control applications is all the control signal goes through the low-pass filter. That kind of smooths things out, because if you get an errant signal in a sensor or who knows what else, and that will immediately kind of smooth out. These are finite duration regions, so it doesn't impact my overall stability. It just makes the transition smoother, so I don't excite fuel slosh and flexing and so forth. So yeah, a little smoothing would be required to implement it, but you have that smoothing anyway, so just take advantage of it. Louis?
Show that our derivative became negative definite.
Negative semi-definite still. We haven't proven, this will never, the derivative we have here is, do I have? No. This one is just negative semi-definite because it's negative definite in terms of the rates, but the states don't appear, sigmas don't appear. So we have to look at extra arguments now to talk about convergence. Here's a, where was I? I'm jumping all over the place. Okay, so we did this. This is kind of I'm just outlining, again, this part you wouldn't be responsible for an exam, but I'm outlining that with extra steps we can deal with the discontinuity and of the MRP description and still argue stability, but you need additional arguments to go there. So let's do an application, because if detumbling, here I'm showing you the control now. I'm just showing you the principal angle. It's a 3D tumble, but the principal angle is an easy 1D measure. I give it a huge initial rate of 60 degrees per second. That's kind of like in skydiving. I remember that. There was once a student I had I was in California working for the summer and helping the local jump masters. And this is formation flying with AFF. So two of the jump masters holding on to the student. They're supposed to go up, down, gently, step off. It was more of a up, down, oh shit, and off they go, tumble. Pushed off so hard, two of us had no chance to recover. We didn't have enough. So I just remember going, oh great. Looked across the student as we're going upside down. He kind of smiles at me and go, okay, let's do it. We completed the flip, stabilized it. The student had no clue. Because you have so much sensory overload, you have no idea you actually did a tumble. But we both just kind of, okay. Sometimes in life it's easy just to keep going and get where you want to get going. Don't fight the air. And that's what happens with this MRP control. We give it a huge rate. Because of the switching, it automatically will go, okay, I'm going to fight this rate up to a point, but once I'm past 180, okay, I will stabilize the short way around now. I don't want to unwind the student and flip him 360 just out of principle, and that's kind of, sometimes we do. But anyway, but that's how it's going to stabilize. But that's the attitude error. So we do get this discontinuity. It happens once. You research your stability arguments, things work. From an angular velocity, you can see there's a kink, because that's where the control changes. I fight really hard, and then I go, you know what? I've got this momentum moving me in that direction. I'm going to exploit that momentum and finish up the revolution until I stabilize where I want to stabilize. So that's the discontinuity in the control that you were asking about. And in real life, you would put a little low-pass filter, something to smooth it out a little bit. Again, that's something we have all the time. So, okay, but that's an application where you see now, we've only talked about global stability. The next step is going to be convergence, so I'll do that in the next lecture. But we do have global tracking. You can put anything in there. You can spell out Coca-Cola with a laser in the sky. Whatever you wish, that's your reference. You throw in the right reference trajectory, and off it goes. So it's extremely powerful, and it has a lot of nice properties that we'll be exploring over the next few lectures.